Alright, so in this video we're building off of our idea of graphing and solving linear inequalities, and we're going to actually start applying those to a concept called linear programming. Okay, so let's go ahead and talk about it. So what's an objective function? An objective something is a function that we want to maximize or minimize. So it's just simply a function we want to maximize or minimize. Okay? And then constraints are just inequalities that we're going to use to limit the part of the objective function that we're interested in. So inequalities that limit the parts of the objective function that we're going to be interested in. I'm just going to say in interest. Okay, and then what's a feasible region? Well, a feasible region is going to be the shaded region that satisfies all the inequalities. So what we're going to have is a system of inequalities, and like we did in the previous video, we're going to shade and solve that system of inequalities by shading, looking for the overlap region. So the overlap shaded region. That satisfies all constraints. Okay, now you might be asking yourself, why is this linear program even important to us? Well, actually, this is used a lot. Okay, so if you work for Ford, you might be interested in how can we maximize our profits. So your business analyst might have come up with this function that models your sales. And if you sell a certain number of Ford Focuses, you have a certain number of profit. If you sell a certain number of F-150s, you have a certain number of profit. But if you mix and match how much of each type of vehicle you have, you can determine how can you maximize your profit. So obviously if you're running a business, you want to maximize your profit. If you're talking about cost, on the other hand, if you're using a function to represent your cost for your business, you can say, all right, well, if I spend this much money on this product and I spend this much money on that product, okay, my cost is going to be maximized or minimized. So obviously, if you're running a business, you want to minimize your cost. So this is used a lot. Okay, it's really easy to do once you understand it, but it's used a lot out in the real world. So it's kind of neat. All right, so optimal solutions. So you need to know this. So if an objective function has a maximum or a minimum, it's always going to happen at what we call the vertex of our feasible region. And we'll talk about that in the example. And then the objective function is going to have both a maximum and a minimum value, always. You're always going to have a biggest value and a smallest value. And that kind of just makes sense. So let's go on and do an example. You can read this on your own if you absolutely want to. All right, so find the maximum and minimum value of this function. So here, this is called the objective function, right here. This is my objective function. Okay, and we want to find the max and min of this function using these constraints. So here, these things right here are called my constraints. All right, so what we're going to do is, just like in the previous video, we're going to graph each one of these linear inequalities. Now, I'm not going to go through the process of how do I know where to shade and all that stuff very much, because we have already talked about that previously. So for the first inequality, x greater than or equal to 0, I know that's just simply the y-axis. Okay, and it's a solid line, and I'm just going to shade everything. I know it has to be everything on this side of the y-axis, okay, because it says greater than 0. Okay, that's pretty easy. The second inequality, y greater than or equal to 0, is just the x-axis. And it's also a solid line. All right. And I know I'm going to just shade above. All right, and then so my last constraint is this guy. But to make it easy for me to graph, I want to get y by itself. So I'm just going to say y is less than or equal to negative x plus 8. Okay, I know my boundary line is going to be solid. And I know I have a y-intercept at positive 8, and my slope is negative 1. So I can just plot a few points really quickly. You know how to do this by now. Okay, go through and plot several points until you get enough to make your line. Okay, and then just connect them. Okay, so it's going to look something like that. And it's y less than negative x plus 8. That's going to be on this side. Okay, if you actually tested a point like we did in the previous video, you would find that's true. So essentially, I'm looking at everything on the inside of this triangle. So what I'm going to do, just clean up my picture. You can do this, or you can maybe just draw whatever you want to do. I'm just going to clean up my picture just a little bit. I do recommend you take your time to do this and make your picture as nice as possible. Because the nicer your picture, one, other people are going to be able to understand it a lot easier. Two, you're going to be able to understand it a lot easier. So take your time, don't rush. Okay, so it's going to be something like that. So I'm looking at everything on the inside of this triangle. Okay, so any point in this shaded region that has red, blue, and green, this is called this shaded region where all three of my constraints overlap. That's called my feasible region. So that means any point that I'm interested in is in my feasible region. That's the kind of the region of possibilities. Where do all the possible values for my company actually exist? And what that theorem just told us on the previous page is that, hey, if there is a maximum and there is a minimum, we know for a fact there's a maximum and minimum, and moreover, the maximum and minimum points live at the vertices. So all we have to do is figure out what are the vertices of this shape. So if this shape happens to be a triangle, sometimes you'll get squares, sometimes you'll get weird shapes, but you just have to find the vertices and test each one of those vertices. So I have a vertice right here at 0, 8. I have a vertice, let's come up and give me a little bit more room. I have a vertice right here at 0, 0. And I have a vertice right here at, looks like 8, 0. So I have 3 points I want to test. And each one of these points is an x and a y. So I'm going to just rewrite my objective function, c equals 3x plus 4y. So c equals 3x plus 4y. And c might represent the cost, our consumer spending, or something like that. I don't know what c represents in this context, because there is no context for this problem. But what I want to do is test each one of these points. So it doesn't really matter the order that you do, so I'm just going to say, all right, at 0, 0. I always like to start at 0, 0 if I have those. So this is my x, this is my y, and I'm just going to plug in and evaluate. So everywhere I see an x in my objective function, I'm plugging in a 0. Everywhere I see a y in my objective function, I'm plugging in a 0. So I have cost is equal to 0 plus 0, which just simply means my c is equal to 0. All right, well, that's one of them down. I just go around and check each vertice. Doesn't matter which one you do next, just be sure to get all of them. So my next one was 8 at 8, 0. So now that's my new x and my new y. So everywhere I see an x now, I'm putting in an 8. Everywhere I see a y, I'm plugging in a 0. So c is equal to 3 times 8, which is 24. And then 4 times 0, which is 0. So c is equal to 24. And then finally, we have one more vertice to test, 0, 8. So now my objective function, everywhere I see an x, I'm putting in a 0, and everywhere I see a y, I'm putting in an 8. So I have c is equal to 0 plus 32. So c is equal to 32. Well, from here, it's really easy to see what's the min. So obviously, c equals 0, that's my minimum. And then c equals 32 is my max. Okay? So if I want to minimize cost, let's pretend that this function represents the cost for my company. If I want to minimize cost, obviously, I sell nothing. I sell, let's say I'm selling hammers and screwdrivers. So X represents the number of hammers sold, and Y represents the number of screwdrivers sold. So obviously, if I sell nothing, then it doesn't cost me anything to make it. Okay? Now here, let's say I'm looking at my cost to produce this stuff. Let's say I sell 8 hammers and 0 screwdrivers. Then it's going to cost me $24 to produce 8 hammers. Okay? My cost is that. Now, if I sell just screwdrivers, then my cost is $32. So I maximize my cost by just selling only screwdrivers. So by doing a combination somewhere in here, I'm going to not sell my max. So my maximum exists up here when I just sell screwdrivers. Okay, this is 24. Okay, it's pretty easy plugging in if there's a context. So the problem just asked us, what was our maximum, what was our min? There we go. And does it ask us anything else? It just says find the maximum minimum values. Now, sometimes they'll ask you where do those max and mins occur? Well, the minimum occurs at 0, 0. The maximum occurs at 0, 8. Simple as that. That's it. No big deal. Okay, so let's try another one. Find the maximum minimum values of this objective function. So here, this is the objective function. And you might want to write that down every time until you're comfortable. These are my constraints. I've got 4 constraints this time, so that kind of implies that I should have 4 vertices, I think. So let's find out if that's true. So the first one, x greater than or equal to 0. I know, again, that's just simply the y-axis. And I'm just going to shade to the right. Everything over here. All right, the second constraint is just the x-axis. That's greater than 0, so I'm going to shade above. Pretty quick. Once you get used to it, it goes really quick once you recognize some of the common constraints. And then the next one, I need to get y by itself, so let's do that. We'll do that one in green. So if y is greater than or equal to negative x plus 5, so my y-intercept is 5, and my slope is negative 1. So draw you in a few points. And I strongly recommend you do several points. Now, my boundary line is solid. It looks something like that. Now, y is greater than or equal to negative x plus 5. So I've got to be careful and maybe do a test point. So let's do 0, 0. Okay, so 0, 0 is here. So everywhere I see a 0, plug in. So 0 greater than or equal to 0 plus 5. Or 0 greater than or equal to 5. Well, obviously that's false. So 0, 0 does not work, so I want to shade above the line. Okay, looking kind of strange right now, but that's all right. And then we're going to do our last constraint, this guy down here. So we have 3x plus 4y greater than or equal to 18. Now I'm just going to get y by itself, so have 4y greater than or equal to negative 3x plus 18. Divide both sides by 4, so I have y greater than or equal to, let's see, negative 3/4 divided by 4. So 18 divided by 4. Let's see, that's going to be 9/2. Okay, 18 divided by 4 is 9/2. All right, so that means, let's see, 9/2, let's see, that is approximately what, 4.5? 9/2 is 4.5. So my y-intercept is going to be somewhere about right here. My slope tells me I need to go down 3 units and right 4 units. So 1, 2, 3, 1, 2, 3, 4. Oops, sorry, it should be right in the middle. Okay, so I have 2 points. That should be enough to do my line. It's going to be something a little like that. right, so we need a shade now. It says y greater than that. So that means we're just going to simply shade above. And so now what we need to do is we need to eliminate all the pieces that, or we need to just erase the pieces we don't need anymore. So I'm just trying to keep what's been highlighted everywhere. Okay, so that looks pretty good. And let's get rid of this. Okay, so again, the more careful you are, the better. And then right in here, this little area needs to be erased. I know I just got rid of my line, that's okay. So something like that. Something like that. Okay, so that's my area that I'm looking at. Now it looks like I don't really have any vertices. Okay, but what we're going to do is realize, hey, this is called what's called an unbounded region. We don't make a nice shape, so this is called an unbounded region. So yeah, you can plug in and find a minimum value, but your maximum values is going to be unbounded because the graph is unbounded. So I could test points all the way out here and keep spending money. There's no limit to what we can do because it's an unbounded region. So unbounded regions are weird. You won't see those a lot, but I just wanted to show it to you just in case. Typically what you're going to see is something nice like this. So test the vertices, okay? If you just want to stick with this example, stick with it. This is a little bit more advanced, okay? The key is that it goes unbounded, so there's no restrictions on how big the cost can get, how big your objective function can get. And that's it for linear programming.